Welcome everybody to the first of several in the track this afternoon. I'd like to welcome our guest, David Weinberger. He is an author and renowned thinker in the space of artificial intelligence and knowledge management. We're very excited to have him here. Without further ado, I'm going to hand it over to David.
Hi, thank you so much, Dave. So I'm going to start up the presentation right away because it was already too long, and then this morning I decided I would add some stuff, which was not a great idea. So I'm going to be going at, I hope, a lightning pace through this because we have a very hard stop, and I'll be in the networking site afterwards. Maybe play. Okay, so you should be seeing my slide. If not, some of my slides, let me know if you're not. So I'm going to talk about a really broad topic, and it's going to be a fairly dispersed talk with a few different sorts of ideas in it. So the outline is this: that first of all, I want to talk about what it means to get knowledge from a system that has no knowledge in it, but still genuine knowledge. And then look at a way in which there may be some interoperation between our old systems of knowledge and our new systems of knowledge. I want to look more, I don't know, deeply but superficially, is that such a thing, at some changes in knowledge's nature, perhaps. And as a test, look at old predictions about what data analysis would do to theory, predicting the end of theory. And the spoiler there is I don't think it's going to end theory. So part one is an extended analogy, which I don't think you need, but I'm going to go through it really quickly. So let's, and it's weird, okay? Just bear with me. You, in this hypothesis, you have an enormous collection of the world's coins. You have many of every coin in the world, and you decide you want to sort them. You look at the problem, it's just too massive, so you decide to build a robot because you're good at that. And it turns out, though, that you have a very full workbench, but you have this weird hypothesis. You do not have any measuring equipment. You can't tell anything about the properties of these coins, and neither can the robot. And so the robot that you build, sort of a meta machine, because it's going to be making a coin sorter. It's going to take a full array that you've given it of all the different sorts of gadgets and gears and ramps and everything imaginable. You've given it all that, and it's going to go through a process. And the process is in some ways really simple, which is it's going to randomly add or adjust a gadget that it's placed into this, what's going to be a huge coin sorter. It's going to then run all of your coins through it. And your coins are in various degrees of condition. Some are mint, some have been found on trolley tracks and the rest of it. It's going to run all of them through it. And it's going to see how well that new change, either a new gadget or new adjustment to a gadget, how well it does in sorting the coins into their proper slots. And depending on the outcome of that, it will fairly randomly make, it's going to assess the accuracy, and then fairly randomly, it's going to try to improve that accuracy by, let's say, just put in a slope in one spot. It's going to try adjusting the slope, making it a little bit higher, a little bit lower, running all the coins through, and keeping the changes that improve the accuracy and moving on from the ones that don't. And this is a gigantic project. It's a ridiculous project, but it works. And you end up with this gigantic coin sorter that has slots and ramps and springs and plungers and heating lamps to adjust and magnets and to pull coins one way or another. You have no idea how it works. It wasn't constructed based on any ideas about how it works, because remember, there is no knowledge of any of the properties of coins in this system, which is why I introduced the machine instead of having you do it. The robot has no idea. It has no knowledge. It's just doing those, that's the algorithm that it's following. And sure enough, it works. So you can put in a coin and it comes out the other side, and it's correct. In fact, you have the robot fix it even more so that it orders the coins within their categories by how certain it is. I'll put that in quotes, but the probability that the coin has been correctly sorted. And as you figured out even before I started talking, this is an analogy, and all analogies are imperfect. This is an analogy to a machine learning system, a training a machine learning system. And the point is that you built this without any knowledge of coins, and it works. It is, in essence, a black box. And you might be able to open it up, as with machine learning systems as well, and see some of how it works, or all of how it works, but there may be some areas of it, and certainly in machine learning models, where, at least as of now, we cannot figure out how they work. There is no knowledge in the box. That's the whole point of this analogy. You don't have any materials for judging the properties of things. The robot is just a dumb robot following a heuristic or an algorithm. And it absolutely doesn't know anything about coins. It just knows about blindly adjusting and fiddling with pieces. So this is a system in which data, which bears some relation to knowledge. I'm not going to talk about that, but I think it's less of a relation than we generally think. I'm not a big believer in the pyramid that puts data, information, knowledge, and wisdom. I'm not a big believer in that, but that doesn't matter. There is data in it that is carving out a machine, much as a river will carve out a canyon as if it knew where it's going, but it doesn't. There's no knowledge in the canyon. There is no knowledge in the model. This is not to say there's no knowledge that comes out of the model. I want to be very clear about that. I'm very positive in most ways about the effect of machine learning. I think it's an amazing, amazing technology. And part of what's amazing about it is that knowledge comes out of it without any knowledge. I want to be careful. Without any knowledge in the model itself. This is so different from our traditional and Western, that's my domain here, is just the West, Western ideas about knowledge, which are epitomized in many ways by libraries and library culture. And so you can see manifest in a library many of these properties of Western knowledge. Knowledge is bound within limits. A book is about something, a discipline is about something. And yet, even though there are these distinctions, the library also makes clear that knowledge is a relational thing. There's no such thing as a book on its own. Books are always in reference and relation to others, even if that's just implicit. Knowledge is relational. There's no possibility of there being a single piece of knowledge. This knowledge in the West, we've always assumed that it's organized and have taken the organization of knowledge as a primary characteristic of it. It fits in to a system. There's a sense of commitment in Western knowledge as well. In libraries and written knowledge and books, the commitment is literally ink settling into paper, but stuff doesn't get published. It doesn't make its way through unless there is a commitment to pushing it through. And that once it's there, then we are in some sense committed to address it in further explorations. It's human scale, it's stuff that we can understand. And yet it is also magnificent. Libraries for sure, but also more importantly, the achievement of human knowledge is astounding and magnificent. It's very different from machine learning knowledge, especially when it has elements of being a black box or is just a black box. And I know there's a huge amount of work being done to try to make these systems explicable. As of now, they are not entirely. There are some that we don't know how they work. Maybe someday we will. Maybe machine learning will continue to get more and more complex over time, especially as systems integrate, and we won't achieve. Nevertheless, at the moment, there are black box systems, and they're so different in almost every way from our traditional idea of knowledge in the West. And one of the things that a library and traditional knowledge shows us is that we believe that knowledge is knowledge all the way down. We build knowledge on knowledge. We justify and explore knowledge by reaching out to more knowledge. We may not know what's all the way at the bottom of the knowledge stack, but we believe that knowledge is basically, it's knowledge all the way down. That is absolutely not the case, I think, with at least some machine learning models. No knowledge inside, but it produces knowledge. Keep in mind, I know this at times will sound like I'm being negative about machine learning, and there's a point at which I will. I'm very much excited by the knowledge that machine learning is emitting. So, and especially since often there is no knowledge inside. But I want to suggest a way in which there may be some overlap between these two types of knowledge. One approach, and there's lots and lots of different ways of doing this. I'm going to talk about the single one, which is a knowledge centaur. So the question has been asked frequently, especially among librarians with whom I have the privilege of hanging out from time to time. Will AI replace librarians, especially when it comes to recommendations? That's often what people have in mind. And you can see why this is a concern. It's because places like Amazon, or we could just say Amazon, does recommendations so well. So if you go online to find this book, really great book, which I recommend to everybody. I edited a book series and it's in it, but I have no financial. It's in the book series because this is a really, really great book. If you order this from Amazon, they'll be very happy to sell it to you, and they'll suggest other books. And the other books that they suggest, you'll see a common theme. They assume, for data-based reasons, that somebody who's browsing or buying this book and other books like it, these are the sorts of other books that make sense to recommend. So I assume that many of you are familiar with the concept of a centaur in machine learning. Just in case, as I understand it, the traditional, if you can talk about traditional examples in machine learning, the traditional example of a centaur is a chess grandmaster who is not playing against a machine learning trained model, chess playing model, but is playing along with one, using one. And the idea of the centaur is that a grandmaster using a machine learning model will do better than either the model on its own or the grandmaster on their own. And that's a centaur. It's a very useful concept. I want to suggest what may be exactly the same thing, but it's a little different, I think, which is the idea of a social centaur. So a social centaur in this case, when you ask the question, will AI replace librarians? I think the answer is, yeah, probably could, because machine learning is pretty awesome, but it is unlikely to, especially commercial AI. And that's for this reason. If you are, I'm going to switch examples from data feminism to a meat cookbook, if that's what you've been buying, Amazon's going to suggest other books about meat, but you can be certain that it will not recommend the 1970s groundbreaking book by Peter Singer, Animal Liberation, which is about the ethical problems with growing and eating meat. That is an unlikely sale to somebody who's buying meat cookbook. So we understand why Amazon isn't making that recommendation. It's going to confirm your interest in eating meat by suggesting more and more cookbooks. That's because Amazon goes for the recommendation of least resistance, right? Which means, put differently, the one that is the shortest distance to a sale, because Amazon profoundly does not care what you buy. It only cares that you buy something. I'm not saying it's evil, although that does sound pretty evil, doesn't it? But that's capitalism, and that's what it cares about. So it's going to suggest the books that are most likely to get you to click and to buy. Recommendations of least resistance. Libraries don't do that, right? Libraries will give you recommend the book of least resistance. So if you've been reading romance novels, Harlequin romance novels, the library, and you turn one back in the library, and you ask the librarian, what else should I read? What should I read next? The librarian is likely to say, oh, well, there's another book in the series, right? That's least resistance, but may also make suggestions like, but there's also this writer also has been writing some other sorts of things that are in a different field, or why don't you try reading those? You love Asimov science fiction, he wrote a book about Shakespeare. He wrote a book about interpreting the Bible. Maybe you'd like those. They will suggest things that are just different enough, not so different that you'll ignore them, the way a barbecue chef is likely to ignore the Peter Singer book about animal liberation, but different enough different enough that you will expand your range, your sympathies, your knowledge, but not so different that you'll reject the book out of hand. And librarians are really good at this generally. So commercial algorithms certainly could figure out a way of coming up with books that are just different enough, but they're unlikely to, for the simple reason that they are commercial algorithms and they want to sell books, not fastest path to a book sale. So this is a place in which I think there's room for a social centaur, in which libraries and AI work together. It's a librarian using AI. I think there are obvious reasons why this librarians would be happy to use an AI recommendation system that recognize the importance to culture and to politics and to human thriving of looking beyond where the rut that we're currently in, the comfortable rut that we are in. And this sort of social centaur, I think, works best, is most plausible when the differences between those intersecting circles have not to do so much with skills, but with an intersection of values, the library's values, which are sort of open Western culture values and democracy values, with the ability to handle scale, to provide a set of skills and capabilities operating at scale, which obviously machine learning can know so many more books than any human librarian can. Of course, they're computers. So that's one way in which maybe not the new knowledge and the old knowledge can make themselves both better in a centaur. But I want to look at also ways in which the idea that we now get knowledge from non-knowledge may matter to how we think about knowledge overall. This is a even less pragmatic piece of it. And this is especially important when we are dealing with black box systems for a couple of reasons. And the first and most obvious one is that if it's a black box system, then we don't even know how to ask it questions, or questions that will get us useful answers. We are used to being able to interrogate knowledge and the systems that we build using knowledge. Michael Nielsen, a really good computer scientist and writer, used this as an example, which is, this was back when the Large Hadron Collider was detecting a boson. And his point was that there is no single person who knows how the LHC works. It's too many systems. It's just too much. But I would add that that's absolutely correct, and it's really interesting. Nevertheless, the Large Hadron Collider we can ask it questions. We can find somebody who can ask it a question. So maybe we have to find an electrician or a chemist or a physicist or whatever. But we can find that person, and that person can explore what went wrong, or a team of people can explore what went wrong or what went right. Our systems have been capable of being interrogated. I suppose there's some exception somewhere, but that's been absolutely the norm for what we build. And now that is not the norm. That is not always the case for machine learning. We are building successful machine learning systems that produce useful knowledge, and we can't interrogate them, at least at this point. Now, this raises very big problems, in part for just general forensics, but also it raises the question of bias, which deserves its own session. I am just going to tip my hat at it because it's so important, but it means that we cannot always look inside the machine to see if bias has crept in terms of how it works. There are other ways of seeing often, because we look at the output for one thing, but we may not be able to tell beforehand by examining the machinery, and we may not be able to figure out where exactly the bias crept in. Huge, I assume everybody here is aware of this. So just move on. Not because it's not important, but because it's just not what I'm talking about today. The second, and I think really astoundingly new piece of this is this knowledge from non-knowledge, is that especially if you talk with regulators, you will hear the phrase, but we don't know how it works. And this is said in a type of panic. I mean, but we don't know how it works. And clearly there are issues about that, as I just tried to say. But the really, I think, deeply frightening part of this to, at least to many people, is that the last bit of it, which is it works. This is a system that is operating on data in such complex analyses and configurations we can't see how it works, but it works. And that tells us something about the world. It seems to be in some ways a better readout of the world than our attempts to do things without machine learning that failed. The stuff that machine learning can do now that we couldn't is an indication that the world, that the machine learning's readout of the world as being incredibly complex, chaotic in some ways, and operating through the intersection of so many small pieces in such particular ways that we can't always predict, but the machines can. That's what the fact that machine learning works and we can't always understand it tells us about our world. And that is a new idea. We are used to living in a world for millennia in the West in which the pursuit of knowledge was the pursuit of laws, of generalizations that apply to everything, that simplify things enough that they apply and explain. For that reason, we have, of the two main sorts of reasoning in the West, we have treated induction as a poor cousin to deduction. And for good reason, understandable reason, which is the standard argument. And Bertrand Russell is the first I know who did this, early 20th century philosopher, well, early mid, who gave the example of a chicken who every day the farmer comes out and throws the chicken some food, and the chicken loves the farmer and thinks that the farmer is looking out for the chicken's welfare, and then until one day the induction fails. Everything in that chicken's experience turned out to be a lie. The induction worked until it didn't. And that is the problem with induction. It was one of the, let's say it's the major problem with induction. So in the West, we have always preferred deduction. That is the pinnacle. This goes back to the ancient Greeks for sure, and very explicitly. And in a deduction, as most or all of you know, I'm using the oldest example, this absolutely standard example. In a deduction, there's a major premise, which applies to lots of things. Oh, I got this. Oh my God, I got this wrong. That's really embarrassing. I've looked at this presentation so many times and never saw I got it wrong. Major premise is that all humans are mortal. Oh, I switched them around. There you go, a master of Keynote. Really embarrassing. I should just end here, but I'm not going to. So a major premise is all humans are mortal. A minor premise is Socrates is a human, and the conclusion is obvious, which is Socrates is mortal. Okay, so ignore the text on the screen in front of you in large type. The major premise is the one that says something about all, some class of things. All humans are mortal. It's a generalization, it's a rule, a law, a definition, any of those sorts of things that you want to call it. And the nice thing about a deduction is that if you know that the major premise, all humans are mortal, is true, and that the minor premise is true, Socrates is a human, you can know with certainty that Socrates is mortal. And that certainty is really what has driven our preference for deductive knowledge in the field of knowledge. Theories are a major premise. Scientific theories are a major premise. And then we put in the minor premises and we get a conclusion. So in this case, if you want to know how fast the coin is going to drop to the bottom of a tower, if you know the major premise is the law of gravity, if you know the minor premise is what the mass of the earth and of the coin is, you know the distance and you know the air pressure, you can figure out the time. You can deduce the time with certainty. So why deduction? Well, because it explains multiple cases, right? What I just said is true not just for the Leaning Tower of Pisa, it's for basically anything, you know, law of gravity just works. Second of all, they are unchanging. And in the West, we have had what has has literally been a religious preference for what is unchanging. The ancient Greeks, where this sort of line of thought began, it wasn't quite religious, but they looked out at the world and they saw that everything is changing all the time. And so there's nothing to know because it's, before you know it, it's changed. And however, there must be laws and regularities, a logos, or reason underneath everything that we can know. And that's where knowledge is, not in the world of the unchanging, but in the eternal stuff that explains the unchanging. This old bias for the eternal shows up in religion. In Christianity, the idea that the soul is the real you and your body is just a temporary housing. We think the eternal is the most real. And deduction also helps us make sense of our world because we have a set of laws, principles, and the like that we can understand and that we can apply, and they explain things. So this is, I think, why we have preferred deduction, but there are problems with it, which I think the age of machine learning is starting to make clear. So that's actually my theme. So the first is, machine learning explains multiple situations, but it does so by skipping details. So I told you what the atmospheric pressure was, but I didn't include in that the minute changes in atmospheric pressure for dropping the coin from the tower, or the effect of the wind that is more or less randomly or unpredictably going to whip through that height. I made assumptions about what it means for the coin to hit ground. Does that mean hitting the grass or and I certainly in that reasoning that I gave you for figuring out when the coin would hit, I did not include the gravitational pull of all of the bodies in the universe, even though they all have an effect on it. They do. We don't care about that effect, but that's sort of the point. So unchanging, yeah, but their application, the laws may be unchanging. Yeah, Newton's laws are still pretty good, but the application of them is always approximate because we skip details, and they're good enough. We don't need to know about the gravitational pull of some body gazillions of light years away to judge when the coin's going to hit, but only because we don't care. So it's approximate enough, but these deductions are always approximations. On the bias for the eternal, well, there's terrible, from my point of view, which I won't go into, there are terrible consequences of prioritizing the eternal over the transitory. For example, there are consequences to favoring the soul, the eternal soul, over the vicissitudes of the body. But this is now a religious discussion, and so I'm going to back away. Nevertheless, one way or another, there are consequences of this worship of the eternal. And that sounded like an atheistic statement. I am not equating the eternal with God. And finally, they help us deductions help us make sense of the world. Yes, they do, absolutely. I'm in favor of all this stuff, but they also simultaneously hide the truth of our experience, which is primarily not a deductive experience, or not one that even looks like it's governed by deduction, because it's so varied and unpredictable and surprising and chaotic, right down to its details of whether you're going to spill your cup of coffee on the way into your office. I mean, it's the truth of our experience is hidden by the truth of deductive thinking as well. Again, I want to be clear, I am totally in favor of science and theory. None of this is an argument against that. Okay, so is perhaps machine learning letting us accept the other side of the coin here? Because both sides are true, pardon me. And this is getting even more and more speculative, if you haven't noticed. So inductions are probabilistic, and that's that's the problem with them, especially if you're a chicken. It's a problem for all of us. And so that's a weakness. But laws in their application are approximate. And that's a weakness too. It's okay, we use both, we need both, and we use them appropriately. Uncertainty, in fact, is either way is a component of knowledge. And as long as we acknowledge that, we are in good shape. So a probabilistic statement is true so long as its probability of being right is right, or its probability of being wrong is right, when it gives you its probability. But the universe consists of particulars. And so one of the ways of testing out what I've been saying, I think, is to look back to 2008, when Chris Anderson, the editor of Wired, published an article that was intended as a provocation that said in 2008, in the era of big data and big data analysis, we don't need theory, we can just do data analysis. And he was poking, on purpose, I think, trying to provoke a response, which was pretty negative from scientists for understandably. Anderson made some empirical statements that we can test, right? That we won't need theory and we won't want theory. And now it's 2021 and big data has gone way further than anybody could have predicted because of the rise of machine learning. So are these statements true? No, neither has turned out to be true, just empirically. They're not true. We still need theory and we still want theory. Scientists use machine learning as in the centaur relationship. It hasn't replaced theory, and there's no indication, I don't think, that it's going to, nor would we want it to, because we still want to understand things. Science and machine learning seems to be forming quite a nice centaur relationship. So I think on that ground, Anderson's article is wrong. And where I want to end is to say that, so theory is still with us, but the other side of the coin may be rising, because knowledge is not just for scientists. It's also for everybody who's trying to make sense of their lives and their world, which is all of us. We all depend on knowledge. And in that regard, taking knowledge that way, laws are simply not enough to make sense of what happens. They're crucial in many ways. I'm not against theories and laws, but they're not enough to make sense of what happens, which is maybe the most important role of knowledge in our culture and in our lives. It's because I'm about to run out of time. We make sense of our lives in that sense through things like stories and conversations and art, and through connection, because we do this collaboratively over the net. This is, in doing so, we pay far more attention, and I think properly so, to the particulars, not to the grand theories, but to the particulars. That's how we explain things. We're not looking for universal laws for the stuff that matters for us. We look at the particulars, which means we look at the differences among things, because that's what makes them particulars. Particulars, by their definition, are different from the other particulars. And so I think, personally, I hope that the rise of black box machine learning may be bringing us to pay more attention to dignify the particulars more than we have, not writing them off as mere particulars while we look for broad truths. We should continue doing that, but we look for sense without applying to laws in our lives, and we have always done this. We try to make sense of our lives and our world without laws, personally, and to try to make sense out of details. But that's exactly what machine learning does. And the fact that we now have a tech that enables this, and that is awesome and producing extremely useful results, it may be that we will feel invigorated in our embrace of the details, of the embrace of the particulars, an embrace of the differences, and of the overwhelmingly complex and unpredictable relationships among them. I think that would be, personal opinion, would be really useful. I made it through. How much time left?
We actually have about 5 minutes left, David.
Okay.
Congratulations.
I could have spoken faster. Sorry.
And so if anybody has any questions, please feel free to put them in the chat in FeedLoop. We'd love to get those in so David can address them. And maybe actually I can start off. You mentioned earlier, and I'm going to paraphrase. It wasn't the marriage between librarian and machine learning, but maybe the relationship between those two entities. Have you seen, in your experience, examples of where it works really well, and any kind of explanation as to why?
Well, I mean, it works all over the place. Because these systems are incredibly useful. So, but as I say, when values are not aligned, I think there's a particular benefit to them. So, I mean, librarians, of course, already use data-based, I don't mean databases, but, data-driven technology to increasingly to make sense of everything from what the best way of organizing an off-site archive is in terms of retrieval time by robots, or by humans for that matter, to figuring out what to acquire and what to the opposite of acquire, to get rid of, because libraries are finding. Yeah, well, there's the acquisition. But, I think it's going to be very interesting in medicine to see what happens there as these systems. It seems like every day, probably less than that, there's another machine learning system that's able to do some diagnostic task better than humans can, and we can't figure out what it's looking at in the scans or whatever in the health records. But it seems to be accurate, at least within the population of the data is being gathered from, which is another question of bias and inequity. In any case, it seems to work there. I think the centaur part of that is going to be interesting to watch, because human patients are increasingly going to be faced with treatment decisions based upon probabilistic, inexplicable machine learning results. And of course, we already do that all the time based on easier to understand factors. We look at genetics, and even though we don't know exactly how the genes are working, we will take preventative care, and sometimes quite drastic, based on that. It's a touch point where, if I had to predict, and I don't, but I will, because it doesn't matter what I say. I think that when a doctor says, look, our black box machine learning system says that you stand some good likelihood, 74% chance of developing type 2 diabetes, and you say, I don't know why, it doesn't make any sense, I'm healthy, etc. We will get more, and the doctor says, yeah, but so far the system seems to be pretty accurate, but it's up to you, of course. We're going to be faced with those decisions, and I think more and more frequently, as those decisions, we get evidence that those decisions are the right ones, we will do it the same way that we take advice from physicians now, even though we personally don't know exactly the science behind it. Develop a trust relationship if the machines earn one. If they don't, then different issue.
Great. We have a couple of questions in the chat here. So from Tanya, how important is it for organizations to have data scientists to understand the data? Since we know from statistics, we can make data results be whatever we want them to be.
Well, I think it's hugely important. And the issue is, as I understand it, way more complicated when dealing with machine learning, because as everybody here I think knows, but I think much of the world does not, the idea of you just pour the data into the machine learning system and it creates the model is really pernicious. And I'm afraid to say I've used that phrase myself. I no longer do, because it implies a magic. And in fact, there are so many decisions made by the developers about how tuning it, all of the hyperparameters. It's an art and a skill. And even more confounding is the requirement that the people for whom the system is being developed be able to specify with extreme explicitness what constitutes a successful output. And that's so hard, not just because people are not used to talking in computer terms. Far more important and difficult is that you want a machine that will help you decide who should get promoted or sort through your job applications. What constitutes a successful employee? That's really, really hard. What are the metrics of it? What are the goals of it? What are the values of it? And there's not going to be agreement about it. And there are going to be trade-offs. And some of those trade-offs are going to have implications for equity, for fairness as well. So just to work your way through those, to understand the difference between, you want more false positives or false negatives, That's not corporate speak at this point. That's not decision maker speak. Data scientists need to be, and from my point of view, for this, desperately need to be involved, and at least some of them need to be able to communicate these ideas to people who are not data scientists, because data scientists, computer engineers overall, generally should not have sole responsibility for deciding what the purpose of a system is and what constitutes the success of the system.
Okay. Another question we have here is from Ed. Thanks for putting this one in. You described the machine learning as a black box based on not knowledge that generates or creates knowledge. Despite the accurate predictions and categorization we see ML systems sometimes create, doesn't this mean that they are actually built on sand? Sort of like a gambler who wins most of the time based on astrology. Sure, it works for him, but it is not based on anything concrete.
So I was with, first of all, very nice summary. I could have shaved 10 minutes off my talk until the very last piece, because it's not based on sand. It's not the machine that's doing it, or let's switch out of the dumb analogy of mine. There is, it's based on data, which is a set of measurements that come from the real world. It is evaluated on the basis of its success. If the odds of a machine learning system categorizing, classifying, predicting accurately over time, I think are just astronomically higher. I have so little math, I probably have this backwards, but than somebody with playing dice or roulette. But the most important thing is that there is a growing science behind this. Sometimes the machines result in inexplicable models that are just too complex, but we do know, because we built the models, we built the architecture, and we specified the algorithms, we specified the hyperparameters, and we did this not on the basis purely of random chance, the way that the stupid machine in my analogy does, but on the basis of an understanding of some understanding of what's going on inside of it, how many layers you need, which ones need to summarize and which ones need to, or generalize and so forth, which algorithms are good for which sorts of problems, what are of the many metrics that could come out of the system during the training process, what might they mean? You have a sense of, okay, if it's overfitting, here's the set of 10 different things we can do, and it's not random if one of them works. So this, but I think the most important difference for me is between sand and these correlations that the system is finding, certainly some of which are going to be meaningless correlations, but it is that the machine learning in doing this is operating the way that the world does, that the world, things happen in the world for immensely complicated reasons. And our approach has been, throughout Western culture, Western history, has been to simplify the problem, because that's all we can do. We're very limited creatures. Now we have a system that doesn't insist on simplifying. I know that it does generalizations and simplifications, but you can give it very complex data. It will find as many and as complex relationships among those pieces of data as it can, so long as those relationships help with a more accurate outcome. And in that sense, it's doing something that reflects something really basic and real about the world, which is the world is really complex. And the metrics, the data that we feed in, inevitably reflect that complexity, because they arise from that complexity.
On that note, I just got a message here. We're about to get kicked off. So thanks everyone for joining today. And David, you left some information on where people can find you on the slides, which anyone can download in the feed loop session here.